Welcome to G Fun Facts Online. At the heart of our strange quantum reality lies a rule that seems absolute. Werner Heisenberg's uncertainty principle. It says you can't know everything about a particle at once. The more precisely you know its position, the less you know its momentum, and vice versa. For nearly a century, this has been seen as a fundamental, insurmountable wall. But what if it isn't? What if we could bend this rule, not break it, to see the universe in ways we never thought possible? Today, we're exploring the science of quantum squeezing, a revolutionary technique that is allowing us to hear the collisions of black holes, build hyper-precise clocks, and redefine the very limits of measurement. Let's start with the principle itself. In 1927, Heisenberg revealed that the universe, at its most fundamental level, is built on probability, not certainty. His famous thought experiment imagined trying to see an electron with a powerful gamma-ray microscope. To pinpoint its position precisely, you need light with a very short wavelength, like a gamma-ray. But a gamma-ray photon carries a huge amount of energy. When it hits the electron to reveal its position, it gives it a massive, unpredictable kick, completely changing its momentum. If you use a gentler, lower energy photon to preserve the momentum, its longer wavelength gives you only a fuzzy idea of the electron's position. You can't have both. This isn't a flaw in our tools. It's a feature of reality. The product of the uncertainty in position and the uncertainty in momentum can never be smaller than a specific tiny number, the reduced Planck constant divided by 2. This idea shattered classical physics and told us that the observer is never just a bystander. The act of measuring helps create the reality being measured. For decades, this principle defined what we called the standard quantum limit, or sequel. It's a baseline level of noise imposed by the quantum world itself, caused by a sea of virtual particles popping in and out of existence in what we think of as empty space. For a normal laser beam, this quantum noise is distributed equally between properties, like its amplitude and its phase. You can imagine the total uncertainty as a circular blob on a graph. The area of that circle is fixed by Heisenberg's principle. But here's the brilliant insight of modern physics. While the area of the circle is fixed, its shape is not. Imagine the uncertainty is a water balloon. You can't change the amount of water inside, but you can squeeze it. If you squeeze it vertically, it gets flatter but bulges out horizontally. This is quantum squeezing. Scientists can create special quantum states where the uncertainty of one property is reduced or squeezed below the normal limit. To balance the books and obey Heisenberg, the uncertainty in the other, complementary property gets stretched out or anti-squeezed. Our uncertainty circle becomes an ellipse. The area is the same, but its projection on one axis is now much smaller. We've strategically pushed the uncertainty into a variable we don't care about, to gain unprecedented precision in the one we do. So how is this done? The key is to use nonlinear optics to create special, correlated states of light. The most common method is called optical parametric oscillation. You take a special crystal and shine a powerful pump laser, say a green one, into it. Inside the crystal, single green photons are split into pairs of lower energy twin photons, for example, in the infrared spectrum. These twins are intrinsically linked. The output isn't a bright beam, but something called a squeezed vacuum, the quantum vacuum state, but modified by these correlated photon pairs so that the noise in one aspect of the light is suppressed. The most spectacular application of this technology is at LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO's job is to detect gravitational waves, tiny ripples in space-time from cataclysmic events like two black holes spiraling into each other. A passing wave stretches one of LIGO's 4-kilometer-long arms and compresses the other by an amount less than 1/10,000th the width of a single proton. The main obstacle to detecting this impossibly small signal is quantum noise. This noise comes from the vacuum fluctuations of spacetime itself, and it shows up in two ways. At high frequencies, we get shot noise, which is the random statistical arrival of photons at the detector. This is basically an uncertainty in the phase of the laser light. At low frequencies, we get quantum radiation pressure noise. This is where the vacuum fluctuations actually give LIGO's 40-kilogram mirrors a tiny, random push, creating a rumbling noise that can hide the signal from a gravitational wave. The uncertainty principle creates a frustrating trade-off here. If you turn up the laser power to reduce the shot noise, you increase the radiation pressure noise. You solve one problem by making another worse. This is where squeezed light becomes a superhero. Since 2019, LIGO has been injecting squeezed vacuum states into its detectors. By preparing the light so that its phase is squeezed, they can dramatically reduce the shot noise, making them much more sensitive to high-frequency gravitational waves. But this came at a cost. The anti-squeezed amplitude increased the low-frequency radiation pressure noise. But the latest upgrade for LIGO's fourth observing run is even more ingenious. It's called frequency-dependent squeezing. Before the squeezed light enters the main interferometer, it's sent through an extra 300-meter-long optical cavity. This cavity acts like a filter, rotating the angle of the squeeze ellipse depending on the frequency. The result is a quantum state, perfectly engineered to fight both kinds of noise. At high frequencies, it remains phase-squeezed to kill shot noise. But at low frequencies, the filter rotates the state so it becomes amplitude-squeezed, suppressing the radiation pressure noise from the mirrors. This allows LIGO to get a broadband reduction in quantum noise, boosting the detection rate of cosmic events by up to 65%. We are literally hearing the universe more clearly by manipulating the very fabric of quantum uncertainty. But squeezing isn't just for light. The same principles can be applied to the motion of physical objects in a field called quantum optomechanics. Here, the goal is to reduce the jiggle of a tiny mechanical object, like a vibrating micromirror or an optically levitated nanosphere, below its zero-point energy, the minimum amount of motion it has even when cooled to absolute zero. Experiments have successfully squeezed the motion of these tiny objects, opening the door to ultra-sensitive force detectors that could probe for new forces of nature or act as translators between different kinds of quantum computers, which often operate at incompatible frequencies. It's a way of bringing the strange rules of the quantum world into our tangible, macroscopic reality. Just when you think it can't get any more mind-bending, a radical new approach has emerged from the world of quantum computing. What if you could sidestep the traditional uncertainty trade-off altogether? A landmark experiment demonstrated a way to measure tiny changes in both a particle's position and its momentum simultaneously, with a precision that seemingly defies Heisenberg. The trick was to use a technique called quantum error correction. The team used a single trapped ion, treating its vibration like a tiny pendulum. Instead of preparing it in a normal squeezed state, they put it into a highly unusual grid state. These states have a weird structure that looks like a lattice of probability peaks. Think of it this way. Instead of a trade-off between position and momentum, the researchers created a trade-off between local and global information. Imagine a clock that only has a minute hand. You can read the minute with extreme precision, but you have no idea what the hour is. You've sacrificed global information, the hour, for incredible local precision, the minute. The grid state protocol does something similar. It essentially gives up knowledge of the ion's absolute position and momentum, which part of the grid it's on, in exchange for the ability to measure tiny displacements from any of those grid points with fantastic precision in both position and momentum at the same time. It doesn't violate Heisenberg's principle. The total uncertainty is still there, but it's been cleverly pushed into the coarse global details that the scientists don't need, allowing them to see the fine details of the signal with stunning clarity. This fusion of quantum computing and quantum sensing is a true paradigm shift. And the applications of squeezing are just beginning to roll out. By spin squeezing entangled atoms, We can make atomic clocks even more stable, which could help us search for dark matter or improve GPS. Squeezed light is also the foundation for a type of quantum key distribution, a method for creating provably unhackable communication channels. And it's even being used to develop subshot noise imaging, allowing us to see fragile biological samples with fewer photons, preventing the light from damaging them. The journey from Heisenberg's declaration of an inescapable limit to a modern lab where that limit is squeezed, twisted, and repurposed is a testament to human ingenuity. We've learned that quantum uncertainty isn't a rigid wall, but a flexible resource, a budget that we can strategically allocate. By quieting the quantum hiss of the universe, we can listen more closely to its secrets. Fundamental limits in science, it turns out, are often not the end of the road, but a signpost pointing us toward a deeper and far more interesting reality. Thanks for tuning in to G Fun Facts Online.